checked you online, and there are too many honors for me actually to enumerate them all. So he's interested these days in social networks as well as smart grid. And today we're going to hear more about network analysis problems that are motivated by smart grid. So thank you.
Thank you, Sophia. Well, good afternoon, everybody. Thank you for coming. As a little reward for that, I was in the Helsinki airport on Sunday and I bought these chocolates. There were way too many for me to eat, so I'm going to pass them around.
Thank you.
I have two confessions. First of all, I think some of you know I'm a recovering dean. I'm here in rehab at the Isaac Newton Institute, so be kind to me, and I'm hoping these chocolates will convince you to do that. And the second, maybe more important, confession is that I'm going to talk about electricity grids today, but there's a tremendous amount that I don't know about power systems. I'm not an expert in power systems. I really more come from wireless networks, social networking, those kinds of things. Background, I'm an electrical engineer, so I did study in the ancient past. I did study power systems, but it was the ancient past. So most of what I'm going to talk about today doesn't have a lot to do specifically with the physics of power systems, but more with the sort of information processing aspects of that. I also should point out that most of what I'm going to talk about here today is joint work with a group of postdocs from my group over the past few years. I'll also mention a few other people, but here I want to mention particularly these. Veronica Belmega, who's now at INRIA in Grenoble, Iñaki Esnaola, who is in Sheffield University, Shomil Carr, who's at Carnegie Mellon, Samir Perlaza, who's at INRIA in Lyon, Lalitha Shankar, who's at Arizona State, and Yue Zhao, who is at Stony Brook. Okay, so these are mainly the people who have done the work I'm going to talk about today. So here's just a little background. First of all, you wouldn't be surprised to know that an electricity grid can be modeled as a network. The nodes in the network are basically loads, generators, and connection points, which are known as buses. And the links are transmission or distribution lines that connect those nodes. It's not fully connected, not all nodes are connected, but a lot of them are. Typical node degree is something like 3 or less. It's also, of course, a graph where the vertices are the nodes and the edges are the lines, and typically those can be weighted. It's a directed graph because power is flowing, and there are weights on those on edges, which typically are related to the reactances of the lines, so electrical properties of the lines. So that's an electricity grid. They go back at least 100 years. More modern is a smart grid, which in addition to the physical electric grid contains, it has an overlay of a cyber network, so sensors, transceivers, so there's a communication network, controls, and so forth. And I'll talk a little bit about some of those as we go through. And an important part of this is that typically is connected through a different network. So there are two networks. There's a physical network, and then there's a cyber network, and they're not necessarily the same topology. So this is an example, probably a prime example of a so-called cyber physical system, and it gives rise to some interesting problems in network analysis. Hopefully you find them interesting, and that's what I'm going to talk about today. So I'm going to talk about several of these, and these are all, the ones I'm going to talk about today are all related to grid state estimation, which is a critical part of grid management. At the end, I'll mention some other potentially interesting problems. And I'll just apologize in advance. I'm only going to talk about stuff that that's been done in my group. There are a lot of other work. I'll give some references at the end, and you can dig in if you want to find more. Okay. All right, so I'm going to talk about four things. Two of them have to do with state estimation with constraints. One is called competitive privacy, where the constraint is a privacy constraint. The other one is just distributed inference in general, where the constraints have to do with communication constraints, inability to exchange large amounts of data to every node. And then I'm going to talk about anomalies, two types. One is failures, so-called cascading failures, where we're interested in the problem of real-time topology identification. So this is where the network is starting to go down, and the goal is to try to detect quickly which lines are down so that you can take action. okay? And then the second type of anomaly is a sort of an attack on the grid. And there, I'm gonna look at the problem of attack construction, which is kind of sort of the counterpart of protecting against attack. If you know what the optimal attack against you is, then you can try to take measures to protect against that. Okay, so those are the 4 problems. And let's just dig right into competitive privacy. So this is joint work with Veronica and Lalitha. So there's a paper that appeared in this is the IEEE journal on selected topics in signal processing. It appeared last year. And I'll mention a couple of other papers, I think, here as we go through too. So here's a motivating example. If you look at the North American power grid, and I don't know how the UK power grid operates, but in North America, the grid is managed by these organizations called regional transmission organizations. And basically what they do is they try to decide each day what the load is going to be the next day. It's a prediction problem. And then they want to be sure there's enough generation to take care of that load. So where I live is in New Jersey, and this is my RTO, PJM, for Pennsylvania, Jersey, and Maryland. It's in a bunker, 100 feet underground in Philadelphia. They're very serious about security there. And you can see that not only is it Pennsylvania, Jersey, and Maryland, but it also covers West Virginia, parts of Ohio, Indiana, and even all the way to Chicago. So it's a little bit broader than just the East Coast. So, this is just a motivating example. This is not something that actually happens in this situation, but I just want to use this as an example to give you an idea of what this competitive privacy is about. So, because these grids are interconnected, because these RTOs are interconnected through the grid, so particularly PJM, which goes all the way out to Chicago, there's interactions in what's happening in one of these RTOs and the other. Okay, so the state of one, the measurements taken in one part of this grid can inform the state of another part of the grid. So there's an interest in sharing information, measurements, if you will, between these RTOs to improve reliability of state estimation. So this is a utility of information sharing. On the other hand, the utility market is made up of private actors, private companies. I think that's true in the UK as well. And so for reasons of economic competitiveness between these companies, there's a privacy concern about sharing information. So there's a so-called privacy utility trade-off. And this is a problem that we've looked at more generally with Lalitha, and this is Rajagopalan, her husband actually, also a research engineer, in a paper that appeared a few years ago in the IEEE Transactions on Information Forensics and Security. So we look at an information theoretic measure of privacy and look at how that trades off with utility. So the problem we have here, though, is a different problem because we have multiple actors, each of which has a privacy utility trade-off. And so this leads to a problem of so-called problem of competitive privacy. We have competitors, they have an interest in sharing information, but they also have an interest in not sharing information. So we can set up a simple model for this. We can think about the state as just being a simple scalar, and the measurements of the RTOs as being linear combinations of scalars plus noise. Of course, you can have a more sophisticated model, but this gives us some insights. For a given RTO, the utility gain from whatever information it gets is the minimum mean squared error it can achieve for estimating its own state. The privacy concern of a given RTO is the amount of information leaked about its state to other RTOs. Okay, so we can measure that in terms of mutual information between the state and whatever information the competitors have. Now it turns out that for the 2 RTO case, we can very quickly see what is the optimal method of information exchange. And it turns out that Wiener zip coding, which is a classical description of optimal distributed source coding with correlated sources, is optimal in the sense of it's the way that information should be exchanged when it's exchanged. It maximizes privacy, that is, it minimizes information leakage for any desired utility at the agents. Okay, so the efficient frontier, if you will, of whatever trade-off you have, is going to be achieved by Wiener zip coding. Okay, this is for two users, two RTOs. Okay, but the competitive nature comes in now because it's not hard to see that when the privacy leakage of one agent, RTO, relates to the distortion at the other RTO. So the more privacy I lose, the better your distortion, right? So it's not a simple trade-off for each RTO, rather it's a joint trade-off in this competitive environment, okay? So how should the agents behave? That is, how much information should they exchange? Well, a natural way to look at that is to look at it as a game and examine this in the context of game theory. So that we will do. So first of all, first of all, I'm going to look at the case where the states are Gaussian and the noise is Gaussian. And I'll just make a point that if we look at basically the information leakage of one actor, and we're going to look at the two RTO case, the information leakage of one actor as a function of the distortion of the other actor is a monotonically decreasing function, okay? So we can think about the action of one of these actors in a game as not how much information they provide, but rather how much distortion they create at the other actor, okay? So it's a simple action set. The action of a given agent is the distortion caused to the other agent, and we'll assume that that's maximally some amount, d bar, say perhaps set by regulation, where each of these RTOs has to have a certain quality of estimation. And then we can look at the payoff for a given agent. It depends on its own action and the action of its counterpart. Again, we're just looking at the two agent case. Is some combination of the information leakage plus the amount of distortion that's it's caused to it by its counterpart actor, which is the second term here. I guess I could be pointing with this instead of the bio pointer. Okay, so this is kind of this is the information we've leaked, and this is sort of the information we've received, if you will. So if we look at a Nash game with these payoffs, it turns out that the only Nash equilibrium is when both actors are at their maximum distortion. Okay, so this is basically a prisoner's dilemma. There's no incentive for either actor to provide more information than is dictated by these maxima. Well, this is a one-stage game. We can also look at a larger situation where the game is going to be played every day. These guys get up in the morning every morning, and they have to decide what generation to bring on, so they're going to do this every day. So we can look at a T-stage game, and we can then turn this payoff into a discounted payoff over T time intervals. But it turns out that if T is finite, again, the only Nash equilibrium here is the prisoner's dilemma solution. That is, this is so-called subgame perfect equilibrium, meaning that it's also a Nash equilibrium for every subgame starting at every time and going forward. Okay. So again, there's not really much to say here except that this game, the way the actor should behave in this case is basically to be as selfish as possible. On the other hand, we can look at the infinite game. We get a different story. Okay, so now if we're going to play this game every day forever, which is really what's going to happen in this marketplace, it turns out that there are, so we can just go back, use the same discounted payoff with T equal infinity, and it turns out that there are non-trivial now Nash equilibria, and they depend on rho, which is the discount factor. There's a whole family of Nash equilibria, and they can be sustained. The ones that are sustainable depend on rho. So the larger rho is, the wider the range of sustainable equilibria, because well, they're going to sustain longer and longer as the forgetting factor is closer to 1. Okay, so this gives us some insight into this game. We can also this idea of the privacy utility game, if you will, with competitors. We can also look at a few other things. For example, we can go back to the original game and add pricing. So that is, we can pay, if one actor pays the other actor for information, then we can basically incentivize any behavior. It's not really that interesting because, you know, if you price enough, then you can get any equilibrium in the set of allowable distortions. We can also set up a common goal game where both of the actors have the same utility function. This can only happen if the regulation required it. In that case, you also get non-trivial equilibria, and the nature of which depend on the coefficient Q. So this is an interesting problem. I'm going to move on because I want to get to the other three problems, but I'll just point out some potentially interesting extensions, these are open questions. One is, I've only looked at m equal 2. Much more interesting question is what happens when m is large. In that case, you might, for example, look at coalition games. So some actors might form coalitions in order to increase their utility. You could also, since if these are human actors, then rather than looking at utility theory, we might look at prospect theory, which takes into account the human nature. And also better models. This is all from a very, very simple model, which doesn't really reflect the complexities of the electricity grid. So I think, before this could be interesting in practice, or any practical situation, it would have to be looked at with much more interesting and accurate models. So I just mentioned that this whole idea of competitive privacy is one that can be looked at in other contexts. First of all, other sensor networks. So if you have, say, multiple actors who are looking for resources, say oil exploration in the Gulf of Mexico, well, obviously, if they all exchange their seismic data, they can find oil more quickly. But they don't want to let the other person find the oil more quickly. So there's a privacy utility trade-off here, and so that kind of problem also fits this framework. Also, sensing with untrustworthy allies. So you're in Syria and you have a radar. You're the U.S. The Russians have a radar. Well, you could trade radar data. You could better localize enemy aircraft or whatever. But they're not trustworthy, or we're not trustworthy to them. So how do you make that? How do you take advantage of that? Well, this is another problem of the same type. Social networking is another problem where this kind of idea can be applied. There, the trade-off, the utility is sharing, and you still have privacy to trade off with it. Obviously, the more you share, the more you get back in sharing, but you don't want to overshare. And e-commerce is the same way. We all give up privacy in exchange for economic benefit, and there's another problem that can be studied in the same context. Okay, well, let me shift gears. I want to talk about one of these other problems, and I apologize, I'm going to have to talk about all these fairly briefly. But now I'm going to talk about the problem of distributed inference, which is not a new problem, but it's a problem that has a certain twist because of the two-network nature that I mentioned before. So what I'm going to talk about today comes from several papers, the most recent of which is this one. This is Shomo Carr. This is Anit Sahu, who's a student at Carnegie Mellon. This is Jose Mura. I think some of you know Jose. And this is going to appear in the IEEE transactions on signal and information processing over networks. Hopefully soon. I have the page proofs upstairs that are a little late. So anyway, so here's the motivation for this. So even if we don't have privacy concerns, there are computational and communication challenges with distributed control. Okay, so one of the innovations in smart grid are so-called phaser measurement units, which are fast sensors that can be deployed out in the grid. The old-fashioned sensors, the SCADA system, sent data very slowly. These are fast sensors, and they produce big data. There are also smart meters, which also produce big data. So there's a lot of data out there. The communication networks can't necessarily keep up with it, and certainly all the data can't be shared with every node in the network. Okay. So another feature is this decentralization of control into so-called control areas, smaller than RTOs, smaller control areas that control what's happening in a local area. Now these control areas need situational awareness. Okay, so an interesting question is, what kind of distributed algorithms can we distribute with these constraints to provide system-wide situational awareness through local information at these control areas? And this is the North American grid. This is an old picture. There's a lot more PMUs So what we want to do is state estimation. It's a distributed problem. And here's a conceptually so again, distributed state estimation goes back at least to the 1970s when I was actually studying power systems as an undergraduate. What makes this problem interesting is that this is the estimation of the state of a distributed system, the electricity grid, through a network where the measurements are connected through another network. So as I said earlier, there are two topologies here. One is the actual physical thing that we're trying to estimate. It relates to the physical thing we're trying to estimate. The other relates to how we can share information. Right? What the local neighborhoods may be different in those two networks. So this is the interesting part of this problem that's different from classical distributed estimation. So we'd like to find distributed algorithms that only need local information. Even when the local control areas aren't observable, we'd like to be able to, through exchange of information locally, to find a global situational awareness. Okay, well here's a measurement model for this. So usually we're interested in the phase angles, voltage phase angles of all the buses in all the control areas. So that's what the state of the grid is. So this is a big vector theta. And each control area, we can assume, has its own local observations observed linearly on this state, where the matrix here is just a Jacobian of the local interconnection. So the real model is nonlinear, so this is a linearization, so-called DC model of the measurement, plus noise. And of course, H is not big enough to completely estimate all of H typically. Theta is not observable in this model typically. So here's a way that here's a type of algorithm we can look at that takes advantage of both types of networks, the cyber and the physical. First of all, each control area, the nth one, is going to iteratively try to estimate the global parameter. So we'll let xn be the state estimate of theta at control area n. And then it's going to estimate iteratively in this way. At time t plus 1, the estimate is the estimate at time t, corrected by the usual innovations correction or residual correction through the observation matrix. Okay, so this is just the residual of the previous estimate, plus another term, or minus another term, which is a consensus term. So this is a term that tries to achieve consensus over the local communication neighborhood of the nth control area. So basically, what has to happen is over your local communication network, you have your neighborhood communication network, you have to exchange estimates each time, and you try to achieve consensus among those estimates, in addition to trying to achieve low residual energy based on the physical measurements that you've got of the physical network. So this is based on the physical network, this correction, and this correction is based on the cyber network. There are coefficients here, this is a typical algorithm. These coefficients have to go to 0, but not too fast. This, by the way, algorithm appears in another paper. This is Le Xi, who's a professor of electrical engineering at Texas A&M, who is a power person. This is one of his students, and this is Shomo, who I mentioned before. And this appeared in the IEEE Transactions on Smart Grid in 2012. So what can we say about this type of algorithm? Well, it turns out that if the grid is globally observable, which just means that this matrix is full rank, okay, so that means that if you had all the measurements from all the control areas, you could estimate theta. And the communication network, so this is a property of the physical network up here, this is a property of the cyber network. If the communication network is connected, meaning you can get from any node to any other node, and that can be tested by looking at the graph Laplacian. If the second smallest eigenvalue is positive, the network is connected. Those two conditions assure almost sure convergence of all these local estimates to global least squares, okay? Provided that the alphas and betas are programmed appropriately. So they have to have certain properties. As I said, they go to 0, but not too fast. you can get almost your convergence to global least squares. Okay, so here's a sort of a general type of algorithm that we can apply to this distributed linear estimation problem. Here's just a simple example. This is so-called IEEE test system. It has 118 buses, so it's just a standard test system that IEEE has put out there on their web. This one has 9 control areas. None of them is globally observable, so none of these control areas can estimate the state by itself. The solid lines are physical connections between the control areas, and the dotted lines, or the dashed lines, are cyber connections between the control areas. There are 2 shown here, but I'm just going to show 1 here, but this just, it doesn't matter which one you use, they're both connected. So the system is globally observable, which is good. These networks are connected. All the control areas are globally unobservable, as I said, and these 5 that are shaded are actually locally unobservable, meaning they can't even estimate their own state by themselves, okay, their own part of theta by themselves. And this just shows some selected phase angles, for some selected phase angles, the convergence of this algorithm to global least squares. Okay, so we know it converges, but this just shows as an example that it does. So the basic idea here is one of distributed observability. Okay, this is a joint property of the sensing model, which is the cyber layer, and the agent network, which in this case is the physical layer of the electricity grid. And that we get distributed observability, that is observability for distributed state estimation, if we have global observability of the physical model and connectivity of the cyber model. Okay, so that's a general principle. And it's been developed further in these papers. Here, we sort of generalize, extend the work of Le Xi to more general linear estimation problems. We look at asymptotic normality and these kinds of problems. This is the Science Journal of Control and Optimization. We also look at learning, reinforcement learning, so Q learning, distributed Q learning. This is the IEEE transactions on signal processing. More recently, we've looked at a problem where we're doing distributed estimation where some of the sensors may be faulty so that we can't trust the measurements, and we can do a combined detection estimation procedure where we're still using this idea of consensus plus innovation. And then finally, a paper that's about to appear, this is the one I mentioned at the first, with Anit Sahu, is looking at the nonlinear parameter estimation problem. So as long as you have, and which is really more applicable in a way in power systems because it is a nonlinear problem, but as long as you have the right smoothness properties and so forth of the nonlinearities, you can get, as you might expect, you can get the same type of results, consistency, asymptotic normality, and asymptotic efficiency. Okay, so let me move on now. I'm just checking the time here. I think I have time to go through everything. So now I want to switch gears and talk about another problem, which is real-time topology identification. And what I'm going to talk about appears in several papers, the most recent of which is this paper that appeared in the proceedings of the IEEE workshop on statistical signal processing in Mallorca in July. This is Yui Zhao, who I mentioned, a former postdoc of mine. This is Ji Chen, who's at Microsoft Research. Okay, so here's a motivation and a model for this problem. So I mentioned at the beginning that the motivation of this problem is really to be able to quickly assess the topology of the grid when you start having failures. Okay, and the idea is it's like fighting a forest fire. You want to know where the fire is going so you can build a wall around it essentially and equip it and have it contained. Well, you can contain cascading failure if you know where it's going by shutting off breakers and so forth around the grid. Okay, there's some famous examples where this has been a major problem. There was a huge outage in the east coast of the U.S. a few years ago. It was one of these cascading failures that started with a squirrel in transformer or something in Ohio and eventually wiped out the whole East Coast. This is the kind of thing they're trying to avoid. It didn't hit Princeton, by the way. Somehow it missed us. But anyway, so the problem with this is that it's a pretty big network, And if you have L lines, then you have 2 to the L possible outage lines. So hypotheses about which lines might have gone out. So it grows fairly rapidly, the complexity of this. So we need some simpler algorithms for determining the topology as it's changing, okay, of the grid. So we can look at a basic formulation here. We can think about measurements, which are functions of the node power injections plus noise. So we look at a linear model. This is actually okay, linear here. M is the incidence matrix, so it just tells us what's connected, what connections are there. S is a vector that tells a vector of binary line statuses. So S equals 1 means the line is connected. S equals 0 means it's down. Okay. So as I said, they're typically they're going to be L of these, and so they're 2 to the L possible values for this diagonal matrix in here. Now, if you want to do inference, Bayesian inference on this topology S, then we need to know its posterior distribution given P and Y. And by the way, this is a simple model. We can also look at a situation where we don't observe the powers directly. We can observe phase angles, and we don't have to observe them all. We can observe a subset. I'm just going to look at a simpler example here. But we don't have to have this full information in order for these things to apply. Okay. So the problem, as I mentioned before, is if you want to compute this posterior, it has combinatorial complexity. So we can't do that in real time if we have a large grid to monitor. So, I mean, this is a standard kind of problem that comes up in a lot of areas, right? Channel decoding and so forth and so on. And the right approach, or the kind of approach that helps us solve this problem, is variational inference, where we approximate somehow the posterior or the system or something in a way that makes it more straightforward and to quickly determine the line statuses. So I'll mention 2 of these. One is to use graphical models and message passing. Okay. The other is to use offline training of some posterior, some approximating posterior, okay, that can then be quickly used to do a line status update online. Okay. All right, so let me mention the first one. This is actually in another paper by, this is G and Yui again. This is Andrea Goldsmith, who's another collaborator of mine from Stanford. And this is just a way of using message passing algorithms in this situation. So I'm not going to go into a lot of detail, but I'll just show you some highlights here. First of all, we have low nodal degrees here, which makes it very easy. All the messages that have to be exchanged, so this is a message passing algorithm, so all the messages that have to be exchanged have very simple formulaic versions. And we can do 3 types of check nodes. Some are physical and some are cyber. Bus check, okay, that's a physical check. Line check, that's a physical check. Measurement check is a cyber check. So there are 3 types of check nodes. This is a simple 3-bus network, but there are other, I mean, in general, you still only have these 3 types of checks. Everything is very low complexity here, and that means this can be done very quickly. And this just shows that through an example, this is a 14-bus grid. A 14-bus grid can have a lot of lines, okay? And this shows the receiver operating characteristics, so probability of detection versus probability of false alarm, or type 1 error versus the power of the test. And this is the receiver operating characteristics for various numbers of measurements. So a PMU is a measurement unit. Okay, so you can see if we have 13 PMUs in a 14-bus system, we're measuring almost every bus, and we can very easily detect, using these algorithms, detect outages, or detect outages. The other idea I want to mention is this idea of learning to infer, which is essentially using a parametric model to approximate the posterior distribution. So we have this posterior distribution. We want to approximate it with a posterior, with a parametric model that is basically represents that posterior close enough and can be easily computed at the same time for real-time inference. okay? Once we have such a parametric model, we can train it using empirical risk minimization. So we want to find the parameters that give us the model that's closest in divergence to the true posterior. And we can do that by maximizing this average where this is a simulated average where the samples are drawn from the true distribution. So this is a standard way of optimizing this kind of parametric model, variational distribution. So offline, we can train this model with as much data as we want. We have plenty of time. And then when there's an emergency in real time, we have a trained model and we can use it very quickly to compute the posterior. To approximate the posterior and then quickly determine where line outages are. So here's an example which comes from actually a paper that hasn't appeared yet. This is Global SIP, which will be in Washington in December, where we use as our model a two-layer neural network. The hidden layer uses rectified linear activation, so it's just 0 for negative inputs and linear for positive inputs. This is the hidden layer. We train this using various amounts of data, and training takes a long time. On a laptop, a half hour, but detection, inference, only takes less than a millisecond. So once you train this model up, which you do offline, then you can quickly make detections. And this just shows for an IEEE 30 bus system, a bigger system, this is actually multiple different types of neural networks with different numbers of neurons in the hidden layer, 100, 200, and 300, versus data size. This is the training data size. So this 200K, 300 is this example right here. And you can see that here we get, with 97% accuracy, identifying these line outages very quickly, okay, with this technique. Okay, so let me then shift gears. I got one more thing I want to talk about, and I've got just about enough time. And I want to talk about the problem of attack construction. Okay, let me motivate that a little bit in context of what we just talked about. We just talked about this idea of outages, right? Cascading failure. And typically we think of that as being something that's random, unintentional, right? So you have a squirrel in Ohio, and the next thing you know, the whole East Coast is out, right? But another problem is a problem where you have malevolent actors. Okay, so this is a homeland security type problem, where you have an attacker who intentionally attacks the network in some way, okay? And there are two types of attacks that are of concern. One are data injection attacks, where the idea of the attacker is to change the state estimates without actually changing the state. So you inject data somehow into the sensing system, the grid manager thinks the state is one thing and the state is another thing, so that can cause the system to go down because the grid manager might take some actions that then compromise the grid. So another type of attack of concern is a physical injection attack, where the idea is to change the state without changing the state estimates. So here you want to inject power somehow into the system in ways that the grid operator can't determine. So this is something a little bit like the Stuxnet, where in Iran, the nuclear refinement facility was going out of control, and the people who managed the facility couldn't tell because their estimates of what was going on were normal. Okay, so this kind of attack, you don't have to be physically there to make this kind of attack. You could implement it by a cyber attack on generation facilities, for example. Okay, but in either case, there's sort of two goals of the attackers. One is to minimize detectability, so sort of unobservability of the attack. Another is to control the complexity of the attack. That is, if you have to attack every node in the network, it's probably not going to be practical. So essentially, you're looking for sparseness of the attack. You want to minimize the number of nodes you have to attack to get a given amount of impact. And then, of course, you want to maximize the impact. So in the case of data injection attacks, that's estimation error. You want to make it as large as possible. In the case of physical injection attacks, you like to maximize the number of nodes affected. Okay, so those are the criteria that the attacker is going to look to optimize. So I'm going to look at just two examples here. One is the sparsest unobservable physical attacks. This is in that paper. This is in a paper that with Yui and Andrea. It's going to appear in the IEEE Transactions on Automatic Control, probably late this year, early next year. And the problem we have here is the problem of finding the sparsest possible set. So it's an L0 optimization problem. We have a linear model. Power injections are related to voltage phase angles through the Laplacian of a graph. The graph is basically the graph I mentioned at the beginning. It's defined by the grid. The vertices are the nodes and the edges are the lines. And the edge weights are inverse reactances. So the reactances are just physical properties that describe the electricity flow in the lines. So we have this simple linear model. This is a linearization, so it's a DC model. And within this model, we want to find the sparsest possible physical attack. So we can set that up in this way. This is basically the L0 norm, if you will. It measures the number of non-zero components, and the attack, so delta P is the change in power injections. We're going to minimize that over the changes in phase. They have non-zero, obviously they can be zero, this can be zero. Non-zero changes in phase. So the change in power injections is related to the change in phase through this graph Laplacian B. And then there's some constraints. So we have meters or PMUs, measurements at certain phase angles. So in order for this attack to be unobservable, the resulting change in phase there has to be zero. And there may also be some unchangeable nodes where the power can't be injected. So these would be buses where they're just crossing. There's no place to put power in, or somehow secure facilities that can't be attacked. Okay, so we can't allow any change in power there. We can't allow any change in phase on this set. Okay, so this is a problem that actually can be examined in the context of this graph that I just mentioned, augmented with edges between all the nodes with sensors. So we have a natural graph, which is defined by the grid, and then we have nodes with sensors in that graph, or some of the vertices are associated with nodes with sensors, and then we also have to connect all of those. So it has to be fully connected. The sensor network part, and we can put any weight we want on the non-zero weight we want on those edges. It doesn't really affect the results. Then it turns out that the sparsest, the minimal sparsity, if you will, or maximal sparsity, I don't know what it is, the sparsest, the number of terms in the sparsest unobservable physical attack is the vertex connectivity of this graph plus 1. Okay, so you can show that. And the number of, for a given vertex cut, even if it could be the minimal one or other unobservable one, it turns out that the impact, that is the number of nodes that can be affected, whose power can be changed, is equal to the number of vertices in the cut set plus the neighbors of those vertices that are away, that do not include measurements. Okay, so any nodes that are away from PMUs, any vertices that are away from PMUs can be added into the cut set as long as they're one neighbors, and that tells us how many vertices or how many nodes can be affected by a given attack. Okay, I've got an example in a minute, but I just want to mention that this idea of sparsest unobservable attack also comes up in data injection attacks. There's an older paper, this is Tong Kim, another former postdoc who works on Wall Street now. And it appeared in the IEEE Transactions on Smart Grid in 2011. And there we also looked at the problem of optimal placement of sensors to protect nodes from these kind of attacks. So you figure out what the optimal attack is, and then you try to find the optimal sensor placement to mitigate the attack. Okay, so here's an example. This is a 30 bus, IEEE 30 bus system. These are the number of PMUs, so these are the number of protected nodes, nodes that are protected by sensors anyway. And you can see that the sparsest unobservable attack has pretty low sparsity. That is, there's 2 and 3 all throughout this range. And then this is the number of buses under power injection attack that you can, the maximum number of buses under power injection attack for each level of sparsity, 2, 3, 4, 5 sparse attacks. You can see that when there aren't many sensors, you can attack almost the whole network. And then as you add more and more sensors, it's hard to attack again, right? Because, well, there are fewer and fewer opportunities to attack when there are more measurements. Another type of attack is a so-called maximum distortion attack. This is data injection attack. This is work with, I mentioned Iñaki, who's at Sheffield. This is Samir, who's another postdoc is at INRIA and Lyon. And this is Oliver Kosu, who's at Arizona State. So we have a linear measurement model. There are various types of measurement model. But basically, when you look at the data injection attacks, typically you look at a situation where the attacker is adding a vector to the measurements. Okay, so putting measurements in, okay, data injection. And then trying to do that in a way that's unobservable typically through least squares estimation. Okay, but if it is observable, there's a problem of trading off the maximum distortion you can get by putting a vector in here and the probability of detection. Okay, so you can find the sparsest attack that can't be detected, but also, but then you have to take whatever distortion you get. But here you can, by looking at other attacks, which might be detected with low probability, you can play with the distortion. So you can trade off distortion and probability of detection, you being the attacker. And there, in this paper, there are 2 problems examined. One is when you have a centralized attacker, so it knows everything about the grid, and it can plan an optimal attack based on the second-order statistics of noise and state, here assumed to be Gaussian, the measurement matrix, and the maximum allowable probability of detection. Okay, so you set a threshold on probability of detection that you can tolerate, and then you can determine what's the optimal attack. We can also look at the problem of decentralized attackers, where each attacker knows only a part of the grid and can attack only a part of the grid. And here we can use a game theoretic formulation to solve this kind of problem with multiple attackers looking for equilibrium attacks. We can also, there's another game theoretic problem that comes up here, and that is when the network operator takes defensive action. Okay, so then you have a game between the network operator as one player and the attacker as another player. And then here, the way the network operator takes action is by using weighted least squares. So it's using a weight matrix and weighted least squares. And the attacker is choosing the attack vector. And then you can set that up. Each has its utility, and you can find Nash equilibrium in that game. And this appeared in another paper with Iñaki and Samir, which was in Global Civ 2 years ago. Okay, so looks like I'm on time, under budget. So here's a summary of what I talked about. First of all, smart grid, I hope you'll agree, presents a number of interesting problems in network analysis. I mentioned these, competitive privacy, where we have multiple actors who have privacy concerns, but would like to share information, they'd like to get information from their counterparts to improve their quality of estimation. So this sets up a game, competitive game, where the payoff has to do with privacy and utility. We also looked at distributed inference, where the interesting thing here is the fact that there are 2 networks, one where information flows and one where physical properties lie. We looked at this problem of real-time topology identification, which is basically a big hypothesis testing problem. There, the solutions are fairly standard. We looked at these message passing algorithms and also looked at approximation of the posterior, and in particular example of a neural network. And then we looked at attack construction, where the main idea is to look at low complexity, looking for sparse attacks, but also talked a little bit about trading off the probability of detection of attacks with the effects of the attacks in the case of data attacks. Some other problems of interest are, I didn't talk about it all, but you might find interesting. One is change detection, so quickest detection. I know Sophie is interested in this problem. I've just started a grant on a DARPA project that's involved with this kind of problem, detection of attacks, quickest detection of attacks. And the things you might want to detect quickly are faults. So you can, the same ideas that we talked about here are ideas that might be applied there. And theft is another big problem. I didn't talk about that, but theft, estimation of theft is another state estimation problem. Theft is a huge economic drag on the power system, particularly in the developing world. And so these kind of things, they're interesting to find algorithms to detect them quickly. The demand side management is a whole host of problems. So demand side means us, the people, the management classically in power network is done centrally by the owners of the resources. Smart grid allows demand side management, meaning management of power usage by the consumer. And the things that come up there are load shifting, trying to make the load. So typically, the load on power system is high in the morning and the afternoon and then low at night. So one way to improve the network, improve the grid, is to shift the load so that it's more even. So there's a lot of work on that problem, how you can do that with minimizing the discomfort and so forth of the consumer. Introduction of storage. So if you have storage, so you have an electric car in the garage, then you can start controlling your battery charging and discharging in a way that can optimize performance. For example, you can use that to shift load, or you can use that to respond to pricing. Pricing is another problem in itself. How do you price electricity to incentivize good behavior? And also the integration of renewables. So renewables produce power when they produce power, and so that's not necessarily when you need power. And so this, of course, closely related to storage and pricing and other things as well. Also, energy trading among microgrids. So microgrids are sort of groups of loads and generation that are sort of decentralized. So you can think about a microgrid maybe as a neighborhood that has a solar array, something like that. So you have multiple microgrids with multiple types of resources and loads. They can trade energy among themselves. This is something that smart grid enables because you have two-way energy flow and communication and so forth. So that creates a lot of other interesting problems, mostly game theoretic problems. So in general, there are a lot of opportunities for solving these problems. So I think I'll stop there and see if there are any questions. Thank you.
When you were doing the real-time identification of the topology and you had the learning approach, was that learning from real network data, or was that learning from a simulation?
It's learning from data simulated with a network topology. So it's not real data. That's
because you have to exhibit all the possible faults, right?
Exactly, yeah. So that's an interesting point, by the way. You notice that in all the examples I use these test systems. And it's very hard to get useful real data. The test system, there are repositories of test systems. There's some very big ones. There's a 4,000 node Polish grid system and so forth. But real data is mostly owned by utility companies, and they're very jealous of sharing that. There's privacy utility trade-off, I guess, and it's all on their side. But yeah, in order to make that work, you have to simulate all faults, right? So it takes a long time. It's a lot of offline training for, so that in exchange for doing quick real-time detection. Good point. Other questions?
I have a question. In the comparative privacy, how sensitive are the game theoretic equilibrium results to the nature of the? So you had this leakage plus log of the distortion.
Yeah. So I mean, that's a good question. I mean, those are chosen because they're logarithmic. They're information information measures are usually logarithmic, but I'm sure you could find others that might give you a different result. I sort of suspect, though, that if it's a realistic kind of an exchange, you're still going to get trivial equilibria in a one-shot game, just because there really is no incentive to help the other person, right? Unless there's some opportunity for quid pro quo down the line, right? So, I mean, you might be able to concoct a utility function that doesn't give you prisoner's dilemma, but I think it's realistic to think that there is a prisoner's dilemma here, right? Because giving information to the other person doesn't do anything for you, right? So it's sort of, it's the way people would behave, or the way companies would behave. Other